Okay, so we just finished the chapter 3 last time. We're going to start a new chapter today. That's higher order differential equations. So we discussed first order differential equation in chapter 2. Okay, so we know how to solve different types of first order differential equations. We have different approaches. But for higher order differential equations, then the method strategy is totally different. And it's much more complicated. So we're going to start the preliminary theory, and that's only for linear equations. You will see how complicated how differential equations are. Even for linear how differential equations. So this section is pretty long. We have to discuss some general theory about linear equations of high order. So it will take quite some time for us to complete this section. So we're going to start the definition of initial value and boundary value problems. Okay, I think we discussed it in chapter 1, but let's just rephrase it again to refresh your memory. So what is the initial value problem? So we have a general higher order differential equation, and we're talking about linear equations specifically in this case, as I already said. So the general form of a linear higher order differential equation will be some coefficient functions on each higher order derivative and the function itself. Okay, so you can write the general form of the equation as an of x times dny over dx to the n, and plus a minus 1x times dn1 y over dx n to the 1, plus all the terms of derivatives of y down to a1 of x dy over dx plus a0 of x times y equals g of x. So in here, an of x, a minus 1 of x, and 1 of x, a 0 of x, and g of x. They are all functions of x. They are not just constants. In general, they are functions of x. And we try to solve for y from this equation, differential equation. So it is a linear because each term on the left is a linear in y, or the derivatives of y. But those coefficient functions, a(x), a-minus 1x, a1x, a0x, and gx, they can be anything. They don't have to be linear. All right. So when we say linear differential equation, it means linear in y or the derivatives of y. But for initial value problem, then we need the initial conditions where we start. So that's defined at x equal to x0. So we just give the initial value for y and the derivatives of y up to n minus 1th derivative. So this y of x0 equals y0, y prime of x0 equal to y1, and so on to y to the n minus 1, y of n minus 1, x0 equals y minus 1. Okay, so you can see This is y0, y1, up to y minus 1. Those are numbers or constants given in the problems for any specified x0. Okay, so those are given. So given the initial values, then we can solve the problem completely. Once again, we want to talk about the solution, general properties of solutions before we actually want to talk about the strategy to solve them. We want to know whether the initial value problem has a solution or not. And if it does, is the solution unique? Those are general questions you want to ask even before you solve it. Okay, so that if there is no solution for the problem, then you don't need to to try to solve it. Or the solution is not unique, then you have to find out which one is the actual solution of the problem. Okay, in reality. So it turns out that the initial value problem for linear differential equation is very simple, so that's the theorem about. It says let nx and minus 1x to a1x, a0x, and gx be continuous on the interval I. Okay, so we want those coefficient functions to be continuous, and let nx not equal to 0 for every x in this interval. So obviously, we want to solve this higher order differential equations, the nth order. So the coefficient function for the leading or the highest derivative of y is not 0 for every x in this interval. That means it's never 0. Okay, in the region we consider. So this nx is never 0 when you map on the whole domain of this problem. Okay, then you just pick up any point x0. So if x equal to x0 is any point in this interval, then the solution y of the initial value problem exists on the interval and is unique. So then that essentially means you give any initial condition for this problem for any point inside the region you consider, then the problem always have a solution. So that's a very very good result for us. So it just guarantees the problem always has a solution, provided that all the coefficient functions are continuous and the leading coefficient function is never 0, right? So let's just look at some simple examples. So suppose there's an initial value problem, 3y triple prime plus 5y triple double prime minus y prime plus 7y equal to 0. So we have a third order differential equation. And all the coefficients are actually constants. 3, 5, -1, 7, they're all constants. Obviously, they are continuous. Constant functions are always continuous. So, and the leading coefficient is 3, so it's never 0. So that tells us this differential equation satisfies all the conditions in the theorem. So according to the theorem, then the initial value problem should have a solution, and the solution is unique. So the initial point we give is at x equal to 1. So we just give the initial value of the function y equals 0 at x equal to 1, and the first derivative of y at x equal to 1 is 0, and the second derivative of y at x equal to 1 is also 0. So these are the initial conditions, and x equal to 1 is in the domain of this problem, or if you want the interval, okay, in this problem, this interval I will be from infinity from negative infinity to positive infinity, because out of the coefficient functions and the gx, which is 0 in this problem, are continuous on the whole real set. Okay, so we can easily identify this interval I in this problem is just the whole number 9. So you can pick up any point for x, that means, and give any initial conditions for this problem. And the problem will always has a unique solution. So that's a strong statement. But the point here is, by inspection, you can easily see that if you let y equal to 0, then the constant function y equal to 0, that's a constant function. So all the derivatives of y will be also 0. So if we plug in that into the differential equation, then the equation is holds. Okay, and if you look at the initial conditions, obviously all the initial values of the function y and its derivatives are 0 for that particular function y equal to 0. So we call that a trivial solution. It is solution to the initial value problem, and it is a trivial solution. But according to the theorem, we know this problem has a solution, and the solution is unique. And we already found one solution for this problem. So it has to be the only solution to the initial value problem, right? Okay. So sometimes you even don't have to solve the problem. You can find the solution of the problem by inspection, and using this theorem to argue that the solution is the one you need. Okay. Does it make sense? Any questions? All right. So that's the initial value problem. So it is quite different from the first order differential equations. Remember? Okay. So another thing I want to mention, or we want to discuss in here, is called the boundary value problem, which is very similar to initial value problem. The only difference is you have the conditions at the boundary instead of at the initial point. You don't have, you're talking about the problem, high dimension problem, and the values at the boundary are given, and this is called boundary value problems, or BVP. So, for example, we are considering a second order differential equation, linear differential equation, specifically here. Although in general we are not, confined to linear problems. So the linear second order differential equation in the general form will be a2x times d2y over dx2 plus a1x times dy over dx plus a0x times y equal to g of x. So this is just the general form we discussed on the previous page in the case of n equal to 2. And then it's subject to some condition y of a equal to y0 and y of b at y of b equal to y1. So the conditions are given at 2 points of x equal to a and x equal to b. So the function value at x equal to a is y0, and the function value at x equal to b is y1. Those a, b, y0, y1, those are constants or numbers given in the problem. So this is called the boundary value problem. You can see the initial condition is different from initial value problem, because in the case of an initial value problem, you give the value of the function and the derivatives of the function at 1 point, x equal to a. But in this case, you are given the function value only, but at 2 different points. You see the difference? Okay, so consequently, the solutions for a boundary value problem will have different properties from initial value problems. So in general, a boundary value problem can have many one or no solutions. All can happen. So we don't have such a theme like the previous page about existence and uniqueness of the solution for initial value problem. We don't for boundary value problems. So that's a big difference between these two types of problems. All right, any questions? So let's just consider several examples where a boundary value problem has different situations where multiple solutions or one solution or no solution occur in different cases. So the first example says, in the following problem, the given 2-parameter family is a solution of the indicated differential equation on the interval from negative infinity to positive infinity. Okay, so the differential equation we have is x squared times y double prime minus y 5xy prime plus 8y equal to 24. So this is a second order linear differential equation. All right. And the solution to this differential equation is actually given. Okay. Y equal to c1x squared plus c2x to the fourth plus 3. If you plug in this function y into the differential equation given the problem, you will see the equation holds. So you can easily verify this solution by plugging y into the differential equation, and you take the derivative and the second derivative, and then plug in everything into the equation. You will see the equation holds. So I'm not going to do that yet. And here we already did that before, again and again. That's easy to do, right? But just accept it. Okay, you can check it by yourself at home. It's not a big deal. Okay, so the question is determine whether a member of the family can be found that satisfies the boundary conditions. Okay, so given this general solution to this differential equation and some boundary value conditions, can we find a solution to the boundary value problem? Okay, so the first case, is the boundary value condition is given by y of -1 equal to 0 and y of 1 equal to 4. So you give the value of the function at x equal to 0, x equal to -1, and x equal to 1. Okay. So we want to know whether a solution to the boundary value problem exists or not. All right. So this is very straightforward. You just plug in -1 for x into the y and the 1 into y, and then try to solve, C1, C2. So y of -1 equal to 0, then you plug in -1 for x into y. You get C1 times -1 squared plus C2 times -4 plus 3 equal to 0, but -1 squared and -1/4 are both 1. So you end up with C1 times 1 plus C2 times 1 plus 3, or C1 plus C2 plus 3 equals 0 from this condition. And then the other boundary condition gives y of 1 equal to 4. So plugging 1 for x, again, you get a y equal to C1 times 1 squared plus C2 times 1 to the 4th plus 3 equal to 4. Okay, again, 1 squared and 1 to the 4th, they are both 1. So the equation becomes C1 times 1 plus C1, C2 times 1 plus 3 equal to 4, or C1 plus C2 plus 3 equal to 4. So you can see that the two equations we end up with, the two boundary conditions are contradictory, right? In the first equation, we require C1 plus C2 plus 3 equal to 0, but in the second equation, C1 plus C2 plus 3 has to be 4. So obviously, this cannot be satisfied. So that means you cannot find such y to satisfy this boundary condition. So there's no solution to the boundary value problem. Good. So that's straight, I guess. So that's the first example. Let's just do the same problem with another boundary condition. Okay, so in this case now we have y of 0 equal to 1 and y of 1 equal to 2. So this time the boundary is given at x to 0 and the x equal to 1. Okay, so what I do, just plug in 0 and 1 for x into y and see what happens. Just do the same thing as we did in the first case. So if you plug in 0 for x into y, you're going to get C1 times 0 squared plus C2 times 0 to the 4th plus 3. And that has to be 1 by the given boundary condition. Okay. But the 0 to any power is just 0. So at the end, you just got zeros for the first two terms on the left, and then you're just left with 3 on the left, and that has to be 1 on the right. And obviously, that's also a contradiction. So you just use one, boundary condition that then concludes there is no solution to this boundary value problem. Again, the boundary condition cannot be satisfied in this case, right? So this problem also does not have solution. All right, let's just see more examples for the same equation. This time the initial condition, we give y of 0 equal to 3 and y of 1 equal to 0. Okay, so again, the boundaries are at x equal to 0 and the x equal to 1, but the values of the function at the boundaries are different now. So just plug in 0 for x and 1 for x and see what you get. So just do it again. if the prime is 0 for x, in y, you're going to C1 0 squared plus C2 0 to the fourth plus 3. And that has to be, oh, wait. 3, okay. It has to be 3 on the right. I don't know why I wrote 0 on the right. Okay, it should be 3. Given by the problem, so y 0 equal to 3. So it's not the equal to 0 in here, but it should be 3. So again, the first two terms just vanish on the left, and so we got 3 on the left and it's 3 on the right. So 3 equal to 3. So that means it's consistent. So it's good. And then we use the other boundary condition y1 equal to 0. So plugging 1 for x in y, so we can see 1 times 1 squared plus c2 times 1 to the fourth plus 3 equal to 0. So that's given. Okay, 1 to the any power is 1. So you end up with c1 times 1 plus c2 times 1 plus 3 equal to 0, or c1 plus c2 plus 3 equal to 0. And so c1 plus c2 will be equal to -3. I don't know why I wrote -1 here. There's so many tables, I'm sorry. So, so we have used all the boundary conditions and we got this equation. The first boundary condition does not give us any new information. It's just consistent with the problem itself. It does not give any information to us. But the second boundary condition does give us a equation with C1 and C2. So C1 and C2 in the solution Y has to satisfy the condition so that the sum has to be -3. Okay. But again, even with that constraint, you can still freely choose C1 and C2 in many different values. You know, as long as the sum of C1 and C2 are -3, that will satisfy the boundary value problem. So you can choose C1 equal to 0 and C2 equal to -3, for example, or you can choose C1 equal to -3 and C2 equal to 0. Or you can choose C1 equal to 5 and C2 equal to -8. So there are many, or infinite many actually, values C1 and C2 to choose that satisfy this boundary value problem. So in other words, this boundary value problem has infinite many solutions. So the solution to this problem is not unique, right? Since you have two variables, C1 and C2 to determine, but you only have one equation to satisfy, right? Okay, so that's another case where, or a different situation where the boundary value problem has infinite many solutions. Let's just do one more example. This time we have the same different equation. Obviously, we know the solution for this equation is the boundary conditions are given at x equal to 1 and x equal to 2 this time, y1 equal to 3 and y2 equal to 15. Okay. So remember, we're trying to solve for y to satisfy these conditions. So just plug in 1 for x and 2 for x and then try to solve for C1 and C2. So if you do that, plug in 1 for x, in y, we got C1 1 squared plus 2 1 to the fourth plus 3 equal to 3 equal to 3. Okay, this time, again, 1 to the any power is 1. So at the end, we just get C1 plus C2 plus 3 equal to 3. And we can cancel 3 on both sides, on the two sides, to get C1 plus 2 plus C2 equal to 0. So that's one equation, or you can rewrite it as C2 equal to negative 1 C2 if you move C1 to the right. And the other boundary condition is y of 2 equal to 15. So plugging 2 for x, and we get another equation. So C1 times 2 squared plus C2 to the fourth plus 3 equal to 15 if we do that. And we know 2 squared is 4 and 2 to the fourth is 16. Okay. So the equation becomes 4C1 plus 16 C2 equals, or plus 3 equals 15. You can actually subtract 3 on both sides to get the 12 on the right. So the equation just simplifies to 4C1 plus 16C2 equal to 12. And then you can use the first equation, C2 equals negative C1, to substitute C2. So we get the 4C1 plus 16 negative C1 equals 12. So that's negative 12 C1 on the left if we combine the two terms, and then you just divide by negative 12 to solve for C1. So C1 will be negative 1 if we do that. And then C2 is just negative 1, so C2 will be 1. So you get the unique values of C1 and C2 in this case. So that means you only have one solution for this boundary value problem, right? So it has a unique solution. So you can see for the same differential equation, if the boundary conditions are given differently, then it can end up with different solutions. So that's what I'm trying to say. And so we just stop here today, and we're going to continue on next time. Any questions?